Okay, let's get going. Any questions about the stuff up to this index-based algorithms? Anything that's not clear to you? Let me know now and spend some time on it before I get into the index-based algorithms. Okay, so so far we've been assuming that the data is clustered and we have no indexes available at our disposal to actually retrieve the data that we care about faster than simply looking through all of it. So let's consider the case where we do have an index. Okay, so we have two forms of indices. One is a clustered index and one is an unclustered index. So a clustered index is one where the data is sort of sorted on the indexing attribute, and so all of the tuples which have the same value of the key are clustered on as few blocks as possible. So for instance, if you have an index on some attribute capital A, all of the tuples with value A is equal to A are going to be close to each other and they're going to be densely packed. So that's sort of the idea behind a clustered index. An unclustered index may be because either that there is no ordering to the data, so the data isn't really ordered by any attribute, or because the data is clustered on a different key. Okay, so the data is either spread out across blocks with no ordering, or maybe the data is clustered on a different key. So if the data is clustered on A, then an index on B is necessarily going to be a sparse index. Okay, it's necessarily going to be not a sparse index, unclustered index. Okay, so it's necessarily going to be unclustered on B if it is clustered on A. So that's just how it is. So let's talk about how do you use indexes for various database operations. So let's start with selection. So sigma. So if you have a selection on attribute small a and you want to check if this small a is equal to some value v, then if you have a clustered index on A, the cost of retrieving all of the tuples with value small a is equal to v is nothing but b of r divided by the number of distinct values of the attribute A. Okay, so v of r is the number of distinct values of the attribute A. Why does this make sense? Well, so think of let's say you have 10,000 tuples, okay, and there are 10 distinct values of A. Okay, so if there are 10,000 tuples, or rather 10,000 blocks of tuples, okay, and 10 distinct values of A. Okay, so if you expect that on average the number of blocks corresponding to each value is going to roughly be the same, then what I would expect is the number of blocks with a certain value of A would be 10,000 divided by 10, right? So it would be 1,000. It's just assuming the uniformity assumption. Of course, there may be some values of A where this is much larger or much smaller, but this is what we can guess a priori without having any other information. Right? So this is just assuming that the values are spread out across all of the distinct values. If you have an unclustered index on A, unfortunately the number of blocks that you would have to consult is in the worst case T of R, so it's spread across T of R, and once again you're dividing by the number of distinct values of A. Okay, so if the number of tuples is, let's say, 1 million, and once again the number of distinct values of A is 10, then it is, your result is going to be 100,000. Okay, so am I missing a zero? I don't think so. Okay, so this is how you would use to estimate the number of tuples or number of blocks corresponding to a clustered index or corresponding to an unclustered index. Now let's try to work through the math here once again. So if I have, this is a slightly more elaborate example. So let's say I have B of R is 2,000, T of R is 100,000, V of R A is 20. the cost of an unindexed selection. So if I was not using an index, if R is clustered on some key, then the cost is 2000 IOs, this is just the number of blocks. If R is unclustered for all keys, then the cost is T of R, the number of tuples, so this is 100,000 IOs. If you have an index on A, and the index on A is clustered, then the cost is B of R divided by V of R comma A, so in this case it's 100. If the index on A is unclustered, then T of R, then the cost, as we saw earlier, was T of R divided by the distinct values, so that's 5,000. Okay, so as you can see in this particular case, using an unclustered index on A is actually worse than simply scanning through the relation if the data was clustered on some other attribute, but this need not be the case in other settings. So for instance, if V of R comma A instead of 20 was 100, immediately this is no longer the case. So it would be, so you have 100,000 divided by, let's say, 100, so you eventually have 1,000, right? And so this is smaller than scanning through the relation if the relation is clustered on some key. Okay, so so the basic note here is that if V of R of A, so this is the number of distinct values of A, if this is small, then an unclustered index is not very useful. It's essentially useless. Okay, so if V of R comma A is large, then an index helps. This makes sense intuitively as well, right? So if you have a large number of distinct values, then the number of tuples for each distinct value is a lot smaller. So if you are selecting on a specific value, then the number of tuples and therefore blocks that you have to retrieve is a lot smaller. Okay, so these formulae are not surprising. It's just if you're assuming that the data is spread out across these values of this attribute, then the more number of values, the smaller the amount of data per value. Okay, assuming the overall size of the relation is fixed. Any questions about this? Any part of this that's confusing? Okay. So let's see how we can use this for more complex operations beyond selection. So let's say I wanted to do a nested loop join, and let's assume that I have an index on S on the join attribute. Okay. So what I can do in this case is I can iterate over R, and for each tuple fetch the corresponding tuples from S. So once again, a nested loops join is basically one loop corresponding to R and one loop corresponding to S, right? So it's a nested loop. Now in this case, you are going to loop through R as usual, and you're going to look up the index for S. Okay, so you're going to use the index for S. So how would that work out? So if the index on S is clustered, so remember the computation for the nested loops, right? So there was a cost for reading R and a cost for reading S a certain number of times, right? So in this case, you don't really need to read S that many times. You need to read S. You don't need to read S as many times as B of R divided by something, right? So in the past you had this factor which was B of R divided by some function of M or N, which is a number of blocks. In this case, it's slightly different. So once again, you have a cost corresponding to reading all of the relation R, and in the internal part of the loop, what you're going to do is you are going to, for every tuple of R, you're going to retrieve all of the tuples of S that match. The number of tuples of, or number of blocks of S that match, number of blocks of S that match, if you're using a clustered index, is what we saw in the previous slide. So it's B of S divided by V of S comma A. This is multiplied by the number of tuples of R. For every tuple, you're going to have to go and do this. Okay? Does this make sense? So essentially, you're looping through all of R. For every one of R, you're going to use the clustered index on A. The clustered index on A is going to retrieve a certain number of blocks of S that match this tuple on the join attribute value. The number of blocks that it's going to match is simply B of S divided by B of S comma A, because this is the number of blocks corresponding to each distinct value of A. Similarly, if the index is unclustered, you simply replace this part of the formula. Instead of B of S, it's T of S. Okay, so the number of blocks is as many as the number of tuples of S. Is this clear? Any questions about this? Okay. Right then. So this formula can actually be pretty bad at times, but I'll let you go look up the textbook for when it'll actually help. So I encourage you to go take a look at the textbook. So I won't be able to cover everything in class. I'm actually one lecture behind. So I'm going to skip over that, but so hopefully you understood the formula, and I recommend that you go read the textbook for when this formula would actually dominate other approaches. Okay, so the last join algorithm that I wanted to cover that uses indexes is the case where both R and S have an index on the join attribute. Okay, so in the previous case, R did not have an index on the join attribute, S had an index on the join attribute. So what you did was you looped through all of R, and for each tuple of R, you would go look up the values of S. In this case, what you can essentially do using the index is to do something that looks like a merge sort. So you can look up all of the values of R corresponding to a certain value of the join attribute, and then look up the same values of S corresponding to the same value of the join attribute, do the join, and then keep doing this, essentially doing a merge sort of, or a merge join of sorts. Okay, so it's like a merge sort, but you're essentially doing a join. So in this case, what you're doing is you're exploiting the two indices to look at the records of these two relations in sorted order. Okay, so essentially it's a merge join. This is the last step of the two-part sorting based algorithm that we saw previously, because in this case you don't really need to do the sorting in advance. The index allows you to skip that sorting step. The index allows you to retrieve the tuples in sorted order. And if you have a clustering index, then the cost is B of R plus B of S, because you're simply reading through R and then reading through S in tandem. The reason why, so due to the way this algorithm operates, it's also called a zigzag join, because if you think about R and S, you read a little bit of R, then maybe you go and read a little bit of S, and then you go back and read a little bit of R, and then you go back and read a little bit of S, and then so on. So that's why it's called a zigzag join, because you're reading a little bit of R, reading a little bit of S, and you keep doing this up until you've computed the join. Okay? Questions about this? It's essentially a merge join. You have indices on both the relations, and you're skipping the sorting step by exploiting the indices on the two relations. All right then. So that's it with the query processing. So let me switch over to query optimization. Okay, so far we've talked about various relational database operators, right? So we've talked about joins, we've talked about selections, projections, and duplicate elimination, grouping, and we've talked about various physical implementations of them subject to various memory restrictions, right? So we talked about two aspects. One is the impact of the memory, and the second is the impact on the number of IOs, or the number of blocks that you have to retrieve or write to disk. So those were the two considerations that we talked about when considering various physical implementations of relational database operators. So the next step is we still haven't figured out how to execute an overall query, right? A query need not consist of just one operator. It's a collection of operators. So how do we execute an overall query? So how do we, in some sense, use these physical implementations in executing database queries? And this is sort of one of the core components of the database engine. This is really what makes database engines tick. Okay, this is really what makes database engines tick, because figuring out how to execute queries is what makes database engines powerful. Okay, so figuring out how to take a given query given by the user, convert it into a strategy or convert it into an execution plan is something that is absolutely crucial to make databases as powerful as they are. So in order to do so, there are a couple of steps. The first step is to take the SQL query, convert it into a logical representation, and this is where relational algebra is going to come into the picture. So this is why we introduced relational algebra in the first place. And second is we convert this logical plan into a different logical plan. So we can transform this logical plan and get a better logical plan out of it, and then find an associated physical plan. By physical plan, I mean a selection for the physical algorithms that operate on the actual data, the kinds of algorithms that we saw in the previous set of slides. And then the query processor is going to execute these physical plans. Okay, so at one level, the logical plan is simply saying, take selection, take projection, take join, and so on. So it's going to be at the level of sequence of operations that are relational. The physical plan is going to take these logical operations and specify how to execute them on data. So it's sort of the actual nuts and bolts of how it's executed. Okay, so that's the separation. So there's a SQL, so you can think of these as three steps. SQL to one logical plan, and then you can transform that logical plan to other logical plans. And then once you have the final logical plan that you've decided on, you can transform it into a physical plan. And this physical plan is then executed. Okay, so, and we'll walk through each of these steps in this lecture and in the coming lectures. Okay, so let's talk about the first step, which is SQL to a logical query plan. So essentially what I'm doing is I'm taking SQL and I want to transform it into a relational algebra expression. Nothing surprising. So let's start with the easy cases. Okay, so the easy cases are the select from where clauses, and in this case my transformation is simply cross product of R1 through RK, followed by a selection condition with condition C, followed by a projection onto the attributes A1 through AN. Okay, simple enough. This cross product could be replaced by a theta join if we want to. That would be equivalent, but for now I'll stay with a cross product. Let's consider a slight generalization. So I have a select from where, followed by a group by. So in this case, I need to use the extended relational algebra, which I didn't introduce, but I've been mentioning over the course of the last few lectures, where here once again you start with the same join of R1 through RK, or the cross product of R1 through RK, followed by a sigma, a selection, right, because you have this where clause, followed by a gamma, which is doing a grouping and an aggregation. So this is one of the extended relational algebra operators. This is the grouping operator, grouping and aggregation operator. Okay, and in this case I don't really need the delta operation because I'm not doing duplicate elimination. Remember that delta was duplicate elimination. So I don't need that. And finally, I have the pi once again for projection onto attributes A1 through AN. Okay, so this is my relational algebra expression for this slightly more general query. Okay, and my goal is to take any SQL statement with nesting, with renaming, with sort of subqueries, all of that, and transform it into a relational algebra expression. That's really what the first step of query optimization does. The first step of query optimization is to take a SQL expression which can be fairly complicated, fairly general, transform it into a relational algebra expression. And it's a extended relational algebra expression because it also has gamma and delta. You can't avoid gamma and delta because those operations can't be expressed as using the other relational algebra expressions. Okay, so like I said, here I'm using the cross product. I could use the join or the theta join if I wanted instead. In most cases, it would actually be a natural join, but I'm going to avoid that for now. So for now, I'm working with the cross product, and that works fine. Yes?
So the relational algebra, is that our logical plan?
The relational algebra is one logical plan, is one logical strategy of execution, right? So what this is saying is, first take the cross product and then apply the sigma and then apply the gamma and then apply the pi. That is one logical plan for executing this query.
So will our logical plan always take the form of relational algebra?
Yes.
Okay.
The logical plan always takes the form of relational algebra. Extended relational algebra, but relational algebra nonetheless. Yes. And the transformations that give you other logical plans will also be just relational algebra expressions. The second step is to take these relational algebra expressions and decide for each operation how it's done on the data. So if you see a sigma, how is that sigma executed? If you see a cross product, how is that executed? And so on. So that's the next step, which I won't get to until later in the class. Okay? Any other questions about this? Okay, so one construct that we learnt about in SQL is that of subquery. So one question is, do subqueries cause problems in converting SQL into relational algebra? And turns out the answer is not really, because subqueries can essentially be eliminated, right? So subqueries don't necessarily even need to be part of your query, because you can replace it with just adding more joins. So for instance, if I had this query with a subquery, so I have select distinct product.name from product where product.maker is in some set. So this is a set of companies where company.city is Urbana. Okay, so here I want to find the products that are made by a company in Urbana. And so one way to replace this with another SQL expression would be to take this and then represent it as select distinct product or name. So once again, the same select clause. And instead of simply doing from the product table, I'm going to do a join between the product and the company table. And I'm going to have so since I wanted to do product.maker is among the set of companies, I will instead have product.maker is equal to company.name. And since I had a where clause here, company.city is Urbana, I'm going to add that as another clause of this where expression. And therefore, I can basically take this subquery and entirely eliminate it and get a select from where expression, and I'm done. Right? So even though subqueries seem to, in some sense, increase the expressivity of SQL, they didn't actually increase the expressivity of SQL. They can be replaced with just a select from where expression. Certainly, subqueries were more convenient to write, but they don't really increase the expressivity of the language. So once again, the first step in any database query optimizer, one of the first steps is to remove subqueries, remove nested expressions, unfold it, replace it as a select from where. Once you have a select from where expression or a select from where group by having an expression, you unroll that and you write it in relational algebra. Clear? Yep.
Is there ever a situation where we have to have subqueries, or can we write all of these SQL queries with just one select from their statement?
You can write all of the SQL queries with just a select from where statement. It can be a very complicated select from where statement, but it will still be a select from where statement. Okay. Yeah. So in some cases, with a lot of the added functionality that SQL provides, the execution of a query might be broken down into two queries, which are both, once again, select from where. Okay. But that's not coming from subqueries. Subqueries don't really add complexity. There are other sort of parts of the SQL syntax that might lead you to decompose this. But ultimately, the claim here is that for the most part, if you know how to optimize select from where group by having, then you're good, because most other things can be transformed into either one or multiple such statements. Okay? Any other questions about this? Cool. So now we have one logical query plan, right? So basically the claim is, given a SQL expression, I can transform it into a select from where group by having type expression. So let's try to make that better. So starting from this, we have two ways of making this relational algebra expression or the logical query plan better. One ingredient is algebraic laws. So these are the ways in which an expression or a relational algebra tree can be rewritten without changing the meaning. This gives us many alternate logical representations for the same initial expression that you started off. And the second one is via optimizations. If there are multiple ways to write the same query, which of those ones do we choose? So once again, there are two things that we need in order, given the space of logical query plans, which logical query plan should we choose? The first thing is, given one logical query plan, I need a mechanism to rewrite it into other logical query plans. Okay? So starting with query plan P1, I need to find a way to rewrite it to P2 to Pn. Right? I need a way to enumerate all of these things. And from among all of these query plans, I need to pick the best one. So I need both the rewriting mechanism and the selection mechanism. Right? I need to be able to rewrite it into one of the many query plans, and I need to pick the best one according to some criteria. And so both of these are things that we need in order to find the best logical query plan in order to execute my query. This still doesn't tell me how to actually execute it, because there's still a step of converting that best logical query plan into a physical query plan, but we'll get to that in a little bit. Okay, so this is just saying there are many different ways. In order to go through those many different ways, I need a mechanism of rewriting. And secondly, from among the many different ways, I need a method of picking one of the ones in order to select and then use that in the next step of my query optimization. Okay, so and there are two ways of optimization. So the first way is via heuristics. So these are rule-based optimizations. These are laws that typically result in cheaper plans, but not always. But for the most cases they result in cheaper plans. So we often end up doing them because in most cases they result in cheaper plans, even though there may be other cases where they don't, a small number of cases where they don't. These are essentially heuristics. Another style of optimization is cost-based optimization. Here we are systematically looking at the size and cost of how much the plans take to execute. So we look at the intermediate results and then search systematically for the best possible plan. Okay? So we will get into both of these in a little bit. So basically there are two styles of optimization. One is a rule-based optimization, which is simply sort of applying rules that I think will improve the cost of the query plan. And second is from among a space of query plans, systematically enumerate them and then try to estimate their cost. Okay, so the three components of an optimizer are the algebraic laws, the optimization component, and the cost-based estimation component. So these two were the two ones that I mentioned in the previous slide. And then the third one is a way of estimating the cost. So the cost-based optimization requires a mechanism to estimate the cost of a certain operation. For that, we need some cost estimation strategy, and I'll get to that in the final set of slides. So this set of slides is going to be on the algebraic laws and the rule-based optimization. The next set of slides is going to be cost-based optimization, and finally I'll get into how do I estimate the cost for a single operation. Okay, if some of this seems confusing, wait until I cover that topic and then hopefully it'll become clearer. So let's talk about algebraic laws. So once again, one of the things that I need is, given a logical query plan, I need mechanisms that will help me transform the logical query plan into other logical query plans. And for this, I need laws that allow me to manipulate relational algebra expressions. Okay? And in this lecture, I'm going to only cover the most basic subset of laws. I encourage you to go take a look at the textbook for a more broader, advanced subset. Here, I'm only going to cover the most basic stuff. Okay, so algebraic laws. Let's first talk about those that hold independent of being a set or a bag. So even if I'm using set relational algebra or bag relational algebra, these algebraic laws hold. So first is commutative and associative laws. So things like R union S is the same as S union R. R union S union T is R union S union T. Right? So this is not very surprising. R intersection S is S intersection R. And similarly, you have another law that allows you to swap the parentheses around. Similarly, you can do the same thing for join. So R join S is the same as S join R, right? The order of the joins don't matter. And similarly, R join S join T is the same as R join S join T. So the order in which you do the joins is actually not important. You can do the joins in any which way you want. And so I'm covering this relatively quickly because they are somewhat obvious, but please try to spend some time staring at this slide once again and try to convince yourself that this makes sense when you get home. Okay? Beyond these obvious commutativity and associativity laws, there are also distributive laws. So this is typically laws that operate over two operators. So if you have R joined with S union T, you can do R joined with S, and then R joined with T, and then union those two. Okay? Make sense? So think of S union T as taking S and T and having two separate tables. You can take that first component and join it with R, the second component and join with R, and then take the union of that. So that's essentially what this is saying. Right? Any confusion about this? Okay. So those are the simplest laws. Let's look at laws with sigma and pi. Okay, so in this case, I'm focusing on set semantics. So as it turns out, sigma and projection work differently for set semantics and bag semantics. So I'll get into that in a second. So the simplest law is for selection is this. Let me write this out first before I explain it. So if you have sigma of condition 1 and condition 2, or condition C and C prime applied to R, then this is nothing but sigma of C and then sigma of C prime of R. Okay, so R with C prime applied first and then C applied next. Or equivalently, it is sigma of C of R intersection with sigma of C prime of R. And the way I usually like to justify these to myself is I draw out a relation R and think about what each of these operations would do. Okay, so if you have C and C prime, essentially what it's doing is it's cancelling out all the tuples that match both C and C prime. Okay, so that was this one. If I wanted to do this instead, I would start once again with the same relation R, and then I would first cancel out all of those that match C prime, and then cancel out those that match C, and essentially I'm going to get the same relation, right? It's not going to give me a different result. It's not very surprising. Similarly, if I do the intersection mechanism, so I would first cancel out those that match C and independently cancel out those that match C prime, and then try to merge the two, right, by doing an intersection. Once again, this is not going to give me a different result. Okay, so these are not very surprising laws. It just requires you to spend a little bit of time sort of working through the intuition for them. Any questions about this? All good? Okay. Move on to the next. So here I have sigma of C or C prime is equal to sigma of C of R union sigma of C prime of R. So the way to think about this, and this we are in set semantics, by the way. So the way to think about this is you have, let's say, how do I show this? So let's say these are all the tuples that satisfy C, and these are the tuples that satisfy C prime. Maybe this satisfies C prime as well. So if I wanted to do sigma of C or C prime, then essentially all of these tuples would be part of the output. Correct? And if instead I did sigma of C of R union sigma of C prime of R, so let me first try to work out sigma of C of R. That would be just this one, skip this one, and this one, right? And similarly, sigma of C prime of R would be this one, and this one. And since I'm doing set union, what I'm essentially going to get is this, and this, right? Which is the same set of tuples as I would have got had I done the left-hand side expression. Okay? Any questions about this? So now let's get into a slightly more complicated one. So if I have sigma of C applied to R join S, my claim is sigma of C can be applied to R first and then join with S. So when do we think that this might be true? So instead of C applied to the selection condition C applied to the join of R and S, here I'm only applying C to R and not to S. So when would this actually be okay? Give me a condition where this might be okay to do. Any thoughts? Okay, let's work through some examples, right? So let's say R was A comma B, S was B comma C. Okay? So, and let's say C was, I'm going to erase this stuff. So R is A comma B, B is S comma B comma C. Let's say the condition C was A is equal to 5. Okay, in that case, can I instead do, is this true or not? Yes? No? So, yep.
Yes, because the condition involves an attribute that's not in S.
Yes, precisely. So it's a condition that involves an attribute that's not in S. It's only a condition on the relation R. So you might as well apply it to R, correct? Okay. So if it was C is equal to 10, on the other hand, you most certainly can't apply it to R, right? Because it's an attribute that's only found in S and not found in R. And therefore, this transformation would not be correct, right? Because sigma of C is equal to 10 of R is essentially the same as R, right? Because there's no attribute C. And therefore, this right-hand side will end up being R joined with S, while the left-hand side is something else. Okay, so if it was C is equal to 10, this is not going to work. It will work for A is equal to 5. Let's consider one last example. What if this was on, what if this was on B? What if it was B is equal to 3? What then? Is this true or not? Anyone? Yep.
I think it's still true.
Still true? Why do you think so?
Because, so in the first case, it's only going to, like we're going to be joining on B, on the attribute B, and so then we're going to choose only those tuples where B equals 3. And then in the second case, first we choose in R the tuples where B equals 3, and then we're going to join on the attributes B for both of those, but we're only going to pick the ones where B equals 3.
Correct, absolutely right. Yeah, you're absolutely right. So if you have a condition B is equal to 3, then you're in good shape. You can actually apply this and this is correct. Okay, so if it's a condition on the join attributes, this is actually correct. If it's a condition on relation R, then this is correct. If it's a condition on relation S, this is not correct. If it's a condition on both R and S, we'll get to that in a little bit. Okay, so this is certainly true when C only involves the attributes of R. If it involves attributes of R and S, we already considered the case of joins or a condition on the join attribute. We will consider a case of a conjunction in a little bit. Okay. Let's also think about differentiation. So if you had sigma applied, sigma of C applied to R minus S, this is actually the same as sigma of C of R minus that of S. So you don't really need to apply a sigma to S again. You only need to apply the sigma to R. And the reason for this is essentially the differentiation operation is trying to eliminate all of the tuples in the second set that are not in the first set. So instead of saying I'm going to do the differentiation operation of R minus S, so take all in R, remove all in S, and then eliminate those that don't satisfy the condition. I can first go ahead and eliminate those that don't satisfy the condition from R, and then subtract it from S. I'm not going to eliminate anything more than I should, because you're still applying the selection condition to R first. And because of that, you're not going to eliminate something that you shouldn't eliminate. So essentially, the same set of tuples are going to be eliminated via the differentiation operation as you would have eliminated in this case. Okay, so I won't get into a formal proof of this, but once you get home, stare at it and try to justify it to yourself. If there are still issues, send us an email or post on Piazza. Okay, so turns out this is true no matter what the condition is. In this case, the condition is going to be on both R and S. R and S has to be have the same schema. This is always true if you are applying set semantics. Finally, we have sigma of R union S is equal to sigma of R and then union with sigma of S. This is perhaps a more sort of not so surprising rule. And also we have sigma of R intersection S is sigma of R intersection with S. So these two rules you should look at and convince to yourself that they are actually, the reason why they are the way they are is similar, and so you can try to think about both of these when you get home. Okay, so these are the set semantics based rules. I'm going to walk you through one rewriting, because this type of rewriting is important for the rest of the class. So let's say I have two relations R A B C D and S with E F G, and I have this sigma F is equal to 3 R join with S. Actually, I'm not going to rewrite this one, I'm going to rewrite this one. So I have A is equal to 5 and G is equal to 9, and I have a join between R and S, a theta join on D is equal to E. And what I want to do is to simplify this as much as possible by pushing down the predicates. Okay, I want to push down the predicates to as close to the relations as possible. And why we want to do that, I'll get to in a little bit. Okay, so let's say I want to simplify this expression. So how would I do this? Any suggestions on what I might do to start?
I have a question.
Yes.
What do you mean by push down predicates?
Okay, so by push down predicates, what I mean is I want to, like I said here, I want the predicates to be as close to the relations as possible. So right now the sigma is happening after I've completed the join, right? I want to avoid that as much as possible. I want them to be applied to the relations directly if possible.
What do you mean by predicates, I guess?
Oh, what do I mean by predicates? Okay, so predicates are simply these sorts of expressions. These are just expressions. So predicates are just expressions.
Okay.
Okay? Sorry, I expected that you might know that from a different class. But yeah, predicates are simply expressions.
Okay.
Yeah. So what I want to do is to take these predicates and I want to push them down into the expression such that they apply as close as possible to the relations. Okay, so I want them to be applied to the relations first as opposed to later on. So how might I simplify this expression, right? So I have A is equal to 5 and G is equal to 9, and I have a theta join between R and S. So first thing that I can notice is that A is equal to 5 applies to R, and G is equal to 9 applies to S. Correct? Okay. So what I can do then is to take this, I can rewrite this by having the A is equal to 5 predicate be applied to R, and then the G is equal to 9 predicate be applied to S, right? And the reason I can do this, is because A is equal to 5 anyway does not affect R, G is equal to 9 anyway, A is equal to 5 anyway does not affect S, G is equal to 9 anyway does not affect R. So I can take these predicates and push them in and have them closer to the relations. And so this expression is essentially going to give me the same result as this expression. Is this clear? So I'm just using the same rules that I talked about in the previous slide to try to move the selections closer to the relations. Okay? So this was what I had for this one. For this one, I'll let you justify to yourself at home that this is the expression that you will end up with. Fun. Okay, so there are a similar set of bag semantics based rules. So it turns out that the set semantics based rules don't necessarily apply to bag semantics. So some of these rules actually end up being changed. So what I would suggest is for you folks to sit and think about these same rules that we declared for set semantics and think about whether they apply to bag semantics or not. In particular, I want you to think about this one, let's say in class right now, and then we will move on. So consider this rule, right? So the rule is sigma applied with the condition C or C prime applied to R is sigma of C of R union sigma of C prime of R. Okay, so this was obvious in set semantics. It was so obvious that we didn't even spend the time trying to formally derive it. Does it hold in bag semantics? No. Why does it not hold?
Because you get duplicates.
You get duplicates. And what sort of duplicates?
You can get duplicates from R and S. No. You can get duplicates from the things that are from C and C prime, and then you can get duplicates from them.
Yeah. So said another way, if you have tuples that satisfy both C and C prime, then those tuples are going to be duplicated, because in the second case, when you're doing independent selection of C, independent selection of C prime, and then you do a union, the bag union ends up having multiple copies of the same tuple, even though you started off with maybe one copy of that tuple, right? Let's say your relation R had no duplicates. The right hand side, if there are tuples that satisfy both C and C prime, those tuples will end up as duplicates. On the left hand side, you will still not have any duplicates. Okay? So the issue with this rule is that this rule doesn't hold because of the issue of duplicates. So similarly, some of the other rules also don't hold. So I want you to think carefully about the other rules on the slide and see which of them hold and which of them don't hold. Okay, so don't even know why this one has disappeared. So let's look at the laws involving projection. Okay. Okay, so the laws involving projection, a simple one is if you have M and N, these are two sets of attributes, and you're applying projections in a sequence, then M intersection N is an alternate way of representing the same projection operation. Why is that? Well, N subselects some set of attributes from R. M further subselects a different set of attributes from R. So the resulting set of attributes are simply those that are common between M and N. Right? So you can't select some attributes from R that don't exist. So you end up sort of each of M and N end up throwing away some of the attributes of R. So the eventual one that you end up with is M intersection N. Okay, so for instance, actually I'll get into an example in a second. So this is a simpler rule. A slightly more complex rule is if I wanted to do a projection on attributes M following a join, then this can be rewritten as a projection on attributes N following a projection on attributes P of R and attributes Q of S. And N, P, and Q are essentially appropriate subsets of the attributes of M that are needed afterwards. Okay? So let's see how this works. So let's say I have this clause or this expression with a pi on A, B, and G, and I have a join between R and S on D. So what can how would I rewrite this such that I push the projection down as far as possible? Once again, like selection, I want to push the projection down as far as possible. How would I rewrite this in order to push the projection down? So notice here that A is part of R, B is also part of R, G is part of S, right? So let me start with something, okay? So let me start with saying, hey, maybe this should be A comma B. Is this correct? And maybe this should be G. Is this correct? Yep.
No, because you still have the D equals E in the theta join.
Exactly. So you still have D is equal to E in the theta join, right? And that, you don't want to eliminate D and E. You need that for the future operation. So you would have A, B, and D here for R, and G and E here for S, right? And then what would be my external expression? Yep.
ABG.
ABG once again, right? Not too surprising. So I still want the same set of attributes to result after this. So I don't necessarily need to do anything further. I just need to use the same set of attributes A, B, and G. Any questions about this? So the thing to remember, at least in projection, is you can push expressions down to the parent relations based on what you need later on, but you need to be careful about the fact that you take into account both projections, joins, selections, all of that need to be taken into account when you push things down. For instance, if you have a selection later on that requires a certain attribute, you can't eliminate that from your projection. You might still need to project that, right? So even though, so for instance, if you had pi sigma and then R joined with S, since this condition C prime may require some attributes of R and S, you cannot eliminate those attributes from R and S if you do a projection push down. When you do a projection push down, you need to make sure that those attributes are still selected. Just like he said, the attributes of D and E are still selected when you are pushing down the projection, because you need it afterwards in order to be able to do the join. Okay? Yes? Okay. Right. So let's move on to rule-based optimization. So the rule-based optimization is basically trying to rewrite the logical plan based on specific algebraic laws, and these laws result in better execution plans most of the time. Okay, not always, but most of the time. So one such heuristic is to simply push selections down, have them apply as close to the relation as possible. In a second heuristic is to, in some cases, pull selections down and then push them back, pull selections up or push selections up and then push them back down. Ultimately, it is still pushed down to have them as close to the relations as possible. Why would we want to do this? The reason why this is useful is because we want to apply the selections as close to the relations as possible so that we reduce the size of intermediate results. By applying the selections right away when you are scanning a relation, let's say you only select 10% of your relation, right? Your selection condition eliminates 90% of your tuples. Then the remaining set of tuples that you need to work with is a lot smaller, and therefore whatever happens later is going to be a lot cheaper. Therefore, since selection conditions are so great in pruning away your data, you don't want to wait until you apply them at the very end. You want to have them applied as close to the relations as possible. You want to throw away as much stuff as you can as early as possible. Okay, so that's the reason behind why I want to push selections down. And the second heuristic is also again pushing selections down, but you can think of this as sort of pulling it up or pushing it up to a point where you understand where each condition needs to be applied and then pushing it to all of the appropriate places. So as a concrete example of the second one, we saw this case where let's say you have sigma of d is equal to 3 of or b is equal to 3 of r, okay, and let me try to rewrite this. Okay, so let's say I have R which is AB and S which is BC, and I have a sigma on B is equal to 3 applied to R. Right, so in this case, I'm certainly reducing the size of R by constraining it to B is equal to 3, but I'm not taking advantage of that B is equal to 3 and applying it to S as well, because I want to reduce the size of S as well. So the way to transform this might be to first pull this selection up and then push it back down. And when I'm pushing it down, here, I don't have space to write this, but I'm going to write it here. Okay, makes sense? So here I pushed it up and then pushed it back down so that I could figure out where B is equal to 3 applies. In this case, it applies to both R and S. And there's a benefit to applying it to S as well, because I want to reduce the size of S that I'm processing. Okay, so this was heuristic number 2, but heuristic number 2 you can think of as a generalization of heuristic number 1. It's just sort of pulling everything up and then pushing it back down. Okay, so let's take some examples. So here's an example of simple pushing of selections down. So I have a projection onto P name, a sigma on price equal greater than 100, and city is equal to Urbana. I have a theta join on maker is equal to name between product and company. Then I know that price applies to product and city of equals Urbana applies to company, so I can push those selections down. So I have pushed this down and I have pushed this down such that the amount of tuples that result at the end of these two operations is a lot less, right? And therefore the join is going to be cheaper and the projection is going to be cheaper. Both of these are going to be cheaper afterwards. So basically the earlier we process selections, the less tuples we need to manipulate higher up in the tree. But there may be cases where this is not beneficial, because then we may end up losing an ordering of the tuples, especially if we want to use an index in the future. Okay, so by applying the selection condition, you're already throwing away any other structural information that you may have about this relation. So if you wanted to use an index on this relation, it may be less useful if you're going to go ahead and apply a sigma first. Okay, so if you want to relate this back to the laws that we looked at, this law is simply sigma of C applied to R join S is sigma of C applied to R joined with sigma of C applied to S. Okay. So let's think about slightly more complex settings involving, in this case, group by and halving clauses. So let's say I have this halving clause which is max of X price is greater than 100, and in this case the query is for each company I want to find the maximum price among its products, but only display these prices if the maximum price is greater than 100. So I want to find all of those companies that sell at least somewhat pricey items. So one way to rewrite this expression is to notice this having clause and say, look, in order for this having clause to make sense, the only tuples I'm interested in are those where x dot price is greater than 100. And since x dot price is greater than 100 is a clause that I can apply early on, I can take this x dot price greater than 100, add it to the where clause. This will help me simplify the intermediate result. It will help me remove some more tuples rather than have to group them and then apply the having clause to them. I don't need to do all that if I can go ahead and eliminate them in the where clause itself. Right? So I can take this having clause and then add an extra condition to the where clause that will allow me to reduce the size of the intermediate results. Is this clear? So the benefit of doing this is that the overall size of the intermediate expression, the size of the join is going to be smaller, and therefore the amount of data that you'll have to manipulate for the grouping expression and the aggregation expression will be smaller. But at the same time, this will require transformation rules that are specific to the grouping and aggregation operation. So in this case, I need to notice that you're looking at max of x price is greater than 100, and therefore you can say that, look, every price that I care about has to be greater than 100. If instead I had average, you think this would still work? No, right? Because here, if I simply rule out all the prices that are greater than 100, I can't compute the correct average anymore, and therefore it's no longer going to work. Similarly, if I try to do min, once again it's not going to work, right? So therefore I have to be careful when I apply these rules, and these rules are fairly tricky, especially if I'm trying to sort of infer the properties of grouping and having clauses and using that to push predicates down or pushing selections down. Yes?
So in the box on the right, since we added the red portion, then do we need the having max statement at all?
Do we need the having max statement at all?
So since we added the red
Uh-huh.
and the x dot price is greater than 100.
You're right, you don't need the having expression. Yeah, you're right. Does that make sense to the rest of you? So you don't really need the having clause, because in this case the and clause as part of the where clause is enough. Yep, you're right. Okay, so let's take an even more complicated example. This is an example of which involves views and pushing selections up and down. So in this case, I want to look at for categories which have some price less than 5, I want to find the company that makes the cheapest product in that category and the price. Okay, so the way I'm going to do it is via two views. So view 1 is basically selecting the minimum price for each category, and I want to ensure that this price there is some price in that category that's less than 5. Okay, so I'm finding the minimum price for each category, and I want to ensure that there is some price within that category that's less than 5. This is simply grouping, this is simply giving me pairs of products or rather companies along with categories and products, or categories and prices. Okay, so I simply want, in this case, I want the company name, the category name, and the price, and I want to then relate both of these views together in this fashion. So once again, the eventual query that I want is for categories with some price that is less than 5, find the company that makes the cheapest product in that category and that price. So for every category I'm finding the minimum price as long as that minimum price is less than 5. Okay, so that's on the left hand side. On the right hand side I'm finding combinations of company, category and price. And eventually here in this join I'm trying to relate both of these two. So I'm taking the results of both of these views and then finding the company that makes the cheapest product in the category along with the price. Okay? So I know this is a little complicated to understand, but hopefully at least you get the general sense. So let's start with what I can do in this case. Okay, so first thing that I notice is that I have this x dot price is less than 5. What can I do with that? Well, I can first sort of move this and have it apply to this overall expression, because I know that since x dot price is less than 5, the minimum of x dot price is also going to be less than 5, and therefore v1 dot min price is going to be less than 5. So essentially I'm pushing the selection up, and then I can push this down as well, right? So here, since v1 dot min price is equal to v2 dot price, I can go ahead and push this down into this view, and therefore I can add another AND clause with x dot price is less than 5. Does this make sense? So this is similar to the expression that we manipulated earlier, where I had this one, right? So this expression, it's conceptually similar to that, where I had some expression being applied to the left hand side. I pushed it up, and then I could apply it to both the left hand side and the right hand side. Similarly, in this case, I'm operating at an even higher level of granularity. I'm operating at the level of views. I find that one of the two views has a where clause. I can take that where clause, move it up to the overall expression for the query, and then have that reflect back once again into the other view. Okay? So these sorts of manipulations are possible, but they are a lot more complex, and therefore in many cases database systems opt for the more simpler rules rather than the more complex rules. So so they often don't use sort of aggregation based conditions to impose or identify clauses that can be applied to multiple relations. Okay, so another way to view this is simply like the expression that I told you about earlier. So you have sigma of C applied to R joined with S. You have this applied to the entire join, and then you apply this individually. Okay, so I'm going to stop here. Any questions about this stuff? Okay, so I'll start with cost-based optimization in the next lecture.